Okay. So I wouldn't know if anybody has question. Okay, since you didn't even watch anything, so you probably don't have question about what we did yesterday. Yes, yesterday we started with regression, and linear regression. We have talked about a lot of concepts, and we have run an example of simple linear regression. So today, let's quickly look at how it looks when you have more than one predictor variables. That is, have 2, 3, or 4 or more independent variables. So the equation, as we said yesterday, that the equation will become something like this. So something like this, y is equal to b0. b0 is the constant, plus b1 x1 for the first variable, b2 x2 for the second variable, and as many as possible to bnsn. That bnsn just signifies as many as possible. Yes. Now, the equation is represented by a regression plane. You see, if it is one variable, that is the predictor, is a straight line. The ones one you have more than one, it's no more a straight line. So if you look at this one has, let's say this one has 2 variables. The picture I'm showing you is an example that was the one that has 2 variables. So if you look and see the plane, one side, the plane figure is a plane figure that has 4 sides now. It's showing you there are 2 predictor variables here. So one will be one side, the other one will be. If there are 2 now, it will be a plane figure that has 6 sides. If there are 3, rather, it will be a plane figure with 6 sides. If there are 4, it will be one with 8 sides. That is the way it is. So if the variable is more than 1, so it gives you something like plane figure. So it will not be something, it will be a plane. It will not be a straight line. That's just the logic. Okay. Now, we want to quickly look at method for multiple regression. Because the same principle is the same principle. So there's nothing, all those fundamental principles, we have explained them under multiple regression. We want to look at the method you use if you are to run multiple regression. Will you just click on the variable and put all of them at the same time? So we have 3 methods generally. We have the hierarchical method or entry. They call it blockwise entry, or first entry, the second one. Or we also have stepwise method. This is stepwise method that is divided into forward and backward. In hierarchical regression, predictors are selected based on past work and decision. In experimental, decide in which to enter the predictor into the model. You know, if you have done the work before, or maybe you read literature, you say that this is the most important one. So just like what we did yesterday about height and pulmonary dead space, imagine if we have more than one variable, and from the previous work that has been done, height is the most important, followed by another one. So we already set a precedent. So it's just for the person to put the height first, then followed by the next one. That is the hierarchical. So hierarchy, they have already classify the predictor according to hierarchy, how important each of them is. So the most important first, followed by the next most important, the last will be the least important variable. That is hierarchical because you have a information before, maybe from literature or from experience that is how it should be. Now we have the forced entry method. It's a method in which all players are forced into the model simultaneously in a situation where you didn't have information. This one is more useful in exploratory analysis. Maybe just stagger at a survey data, and you just see a lot of variables that may serve as predictor. So you just bring them in. That's first entry. Well, this type of thing, sometimes you may not be able to make head or tail from it if you don't understand the variable you are dealing with. Stepwise method, the third one, we get to see all of them also. Somehow they are stepwise. Even the hierarchical is stepwise. It's stepwise, but it's a special form. But when you say stepwise here, you decide about the order in which predictors are entered into the model based on the purely mathematical criteria. What we mean by mathematical criteria? If you do simple regression for each of the variable, you'll be able to know which one. That is what I did for the lady that I ran the peak expiratory flow rate for. So when we first of all do simple regression, the arrow square for each of them will give you how important each of them is. The arrow square. So that one will inform you of which one is the most important. It's not a matter of maybe somebody has told you or you read in literature, but it's what you are seeing in your own data set. The one that has the largest or biggest arrow square will be number one. You put in, after you have done simple regression. Simple. So that is, yes, that is, though that one also, there are two ways. For the stepwise, it can be forward method or backward method. In forward method, you put in the one.
Close that stuff.
In forward method, you put in the one that has the highest, the biggest, or the highest R square. So, followed by the next one. Is forward, but backward, you put in everything. Now begin to remove the one you think is least important to see. The one that will not, the one you remove, it doesn't change the R square much. Or it doesn't even change it. You remove it completely. That is backward. So people, if you compare that forward and backward, some people advocate for the backward because there are some issues you may have with the, we'll discuss that, an issue we may have with the forward method. When we come to some diagnostics, we talk about those issues. So I think we'll move forward. When we talk to that assumption, yes. Assumption, let's talk about the assumptions of conducting the multiple regression. What are the assumptions? Because multiple linear regression, there must be some assumption. Just like, somebody was asking a question yesterday, what is the non-parametric counterpart? You know that a linear regression is a parametric analysis in the sense that there's an assumption that the outcome variable is continuous or is unbounded. So it's on at least on interval scale, at least either interval or ratio, and it's unbounded. So just like the way you have assumption for using parametric tests, this one has its own assumption also. It's only that apart from the assumption for using parametric tests, it has some other assumptions. So all the assumptions for using parametric tests are there, but other assumptions are here. Variable type, all predictor variable must be quantitative or categorical with two categories. And the outcome variable must be quantitative, continuous, or bounded. Can you see? The outcome variable must be continuous or bounded. The meaning of unbounded is there should not be limit. And that is why you got to see that logistic regression, why you cannot use a linear model directly unless you modify it for the categorical variable, because it's bounded. Even when you are talking of when something is measured in percentage, that's how you report, you summarize qualitative data in percentage proportion. It's bounded because the proportion cannot be greater than 100%. That is, 1 cannot be greater than 1. So it's bounded. If they say a value of something can be from 0% to 100%, it's bounded. Or maybe you have a ordinary scale that is from something to 10. So there's a limit to the value of the outcome. So in linear regression, it's recommended that bounded. So if you look at it, all predictor variable must be quantitative or categorical. That's predictor. So you see something. It's funny, in both linear regression and logistic regression, the predictor variable can be continuous, can be categorical. Can you see now? So what differentiates category logistic and linear regression is the type of outcome variable. For linear regression, it's continuous, quantitative, continuous, and unbounded, while the other one, regression, is categorical. That's all. Their predictor is the same. So the predictor for any of them can be quantitative, continuous, categorical. But the categorical must be in 2 categories. That is, we are talking of predictor now. The categorical must be in 2 categories. It must be 1 and 0. That is the logic of dummy variable. So whenever you want to use categorical variable for regression, any form of regression, any form, either linear or continuous, linear or logistic, you must create a dummy variable. You must create dummy, and then that dummy is coded 101010. That was what we did. We still look at it today. Well, we did that when the first day, because Dr. Ikobo raised the issue during the lecture on Thursday, that how do we create the dummy? How we created the dummy with SPSS. You can, because if the data set is not much, you can use and to create it. You can just type it there. And when you're talking of sample size, it's very few. But when we are now talking of large sample size, it's waste of time. Just the way we did it, you just select. So, and once you select, and the funniest thing is that the way you select, that is the one you select, you give you 1. The one you didn't select, give you 0. So it's a way of creating dummy. And if there are many categories, maybe it's if it's a nominal something, even the category, if the category naturally is more than 1, whether if there are 3, you create 2 category dummy. But in some situations, it's advisable to even make sure that it's only 2. You create 2 categories. Yes. It's advisable to create 2 categories. For example, if you have maybe ethnicity, and you have 4 categories, and you want to create dummy, and the significant with chi-square, I want to include in your regression. So it's wise, instead of you say, okay, you are using one category as if you want to create the dummy for, there are 4 categories, like in Nigeria, we usually have Hausa, Igbo, Yoruba, and others, 4 categories. And you now want to use one category as the reference. Most of the time, it's the category that have the least of the attribute that you are looking for, that you make as reference. In that case, 4 category, then you are creating 3 dummy. But it's advisable if you can help it to see if there is one category that has the attribute extremely higher than the other. You just bring it out as one and use the other as reference. Or the other way, maybe there's one category also that have the value maybe extremely lower than the other. You can use as the as the reference and use the other one as the. So in that case, you have dichotomized it. You have already make it 2 categories. It make it easier to interpret and to run Now, if it's okay, don't let me talk about because when you get to logistic regression, there's some special consideration you give to logistic regression. That's if the attribute you are studying in the if it is logistic regression, if the exposure variable is ordinal, you just use it like that. Like educational status, then you can just code it 1, 2, 3, 4. They'll make sure that they are in order. The educational status where you have no formal, primary, secondary, tertiary. But you have to be careful. Sometimes you have educational status of after you say primary, secondary, tertiary. So you now put Islamic. The Islamic, if you code it 5, you are trying to say that it's higher than the tertiary because you are going to enter into error. So the best way to that Islamic, you must be able to put it somewhere. Those people that are Islamic, is that Islamic is equivalent to no formal education, or you want to leave it as primary or secondary? You must, so that you won't just go and give it. You cannot code no formal education 1 is 1, primary 2, secondary 3, tertiary 4, and now say Islamic education 5. And you want to learn regression. If you want to, if it's just for frequency, no problem. But if you now want to use it for regression, it's an error, because what you are saying that the highest level regression is Islamic in that sense, because you have put it 5. So you must now go and bring that one to conform. Either you can put that Islamic as number 1, if you feel that it's the same thing, you merge it with no formal, or you merge it with primary. Should maybe equated to primary. So people, they say no formal education, non-formal education. But all those ones, that one doesn't have meaning in running analysis like regression. Because what is no formal, non-formal? So what we want to know that, okay, the non-formal, will you put it less than primary? Because if you code no primary, no formal education 1, then which is the first step, the first level, the second level, primary. The non-formal, unless you want to put it, is it less than primary, or put it somewhere less than secondary? In that case, you may have to say 1, 2, 3, 4, 5. You make no formal education 1, 2 primary education, non-formal 3, secondary 4, tertiary 5. You must be able to put them in hierarchy. In that case, you can run it like that without even creating dummy. It's just for you to know. But that one is applicable when you are doing logistic. You cannot do that with linear regression. So the categorical variable must come at 0 and 1 in linear regression. Now, non-zero variance. When we talk about variance, talk about measure of variability. The predictor should have some variation value. The regression, if you look at it, it's more like arrangement. That's selecting. Now trying to align the participant or the subject into groups, especially when you're dealing with logistics. But the same thing with this. So if there's no variability in the value, it's just like you want to run regression. All of them have the same value. If there's no value, you cannot run it. There must be variability, non-zero variability. You cannot have a variable that is only one. Maybe you are asking if somebody hypertensive. Nobody is hypertensive. No, nobody is hypertensive. All of them is no hypertensive. You cannot use it for what? Because that one, there's no zero variance in the sense that it's only one value. So no perfect multicollinearity. This one is very, very important. We'll see it as we want to practicalize it. Multicollinearity. Okay, let's talk about collinearity. Collinearity just means two variables that perfectly correlate. Two variables perfectly correlate as their correlation coefficient is 1. So in that situation, if you now have some variable that perfectly correlate there, you are putting them inside the something. That's multicollinearity. So if two variables are perfectly correlate. That shows that they are one. They are serving as one. So, so in fact, if you put them from experience, you put it, if you put both of them, it's only one that will come out. You won't see the rest. It will not come out because it has fit into the other one. So, multicollinearity should not be there. Predictors are uncorrelated with external variables. This one is a difficult one because that's what usually happens if somebody did not do extensive literature review and has not included those factors they're supposed to include. You just have impression that, oh, this variable, oh, after you have done your correlation, is a factor. Whereas this variable correlate with another factor. Maybe that one is even the real factor. So it may be the real factor, maybe the confounder. Or this one is a confounder, somehow, this variable. So if you put in, that one is a matter of, this one is difficult to assess. There should be no external variable that correlate with any of the variables included in the regression model. External variables are variables that have not been included in the regression model, which influence the outcome variable. So most of the time, it's either you didn't include it, it's in your data set, or it's not even your data set, you didn't even collect anything about it. Well, you know that one is difficult. How do you know? If you have not done extensive literature, you will not know. You will not know to exhaust what are those factors. Sometimes also when you may have a clue about this, if by the time you do your this thing and you see that with all the effort, your R square is so small, that shows that there are some lot of variables that are even factors that you have not included. Or maybe there are some also that may even be, even the one you say you have found now, maybe they are not, they are even some other variables that are confounding for it. They are not actually real factors. So, but even in some situations, if the thing highly correlates, or you are able to see that it looks like a good factor, if you have not done extensive data, you will not know maybe it's not a real factor, maybe something else confounded for it. So that is why statistics is not everything. So it's just an instrument. It's not everything. So you need the knowledge. You need the knowledge of what you are doing. You have done extensive literature. Make sure the real factors are there. Homoskedasticity. There should be homoskedasticity. The opposite of homoskedasticity is heteroskedasticity. And this thing can be written, this C also, they can write it as K. You can see that K is the same thing. You either write it as like this, or I put instead of K, it is call it the same way. So this one, you know, in other analysis you are doing, other parametric analysis you do, you want to ensure that the variable follow normal, that there is homogeneity of variance in the variable. That's one of the assumptions of using parametric. But that homogeneity of variance is not important in regression, but what replaces it is the homoskedasticity. The homogeneity of variance is called homogeneity of variance. Homogeneity. Heterogeneity. But this homoskedasticity, this one is talking about the residual. The residual, you know, we have already understood residual. Residual is the error. That is when the difference between the actual value, observed value, and the predicted value is the residual. So the residual should be the same across all the level of X. I think there's a picture there so that make it to make sense. Yes. Look at this. Homoskedasticity versus heteroskedasticity. And if you look at it, as the X increases across, you can see across, you will see that the Y, you will see this is residual, it's not the Y per se. This one, X versus residual. The vertical is the residual. the vertical is the residual. It's not y, it's the residual. Of course, there is the difference between the projected value of y and the observed value. You will see that across it's like as if it's working the two, but this one like a funnel. So the variance is the variation. When we say variance, if you remember variance, that is, if you draw the regression line, how far are they from the regression line? That's the residual now. So if you look at it, as the S increases in this heteroscedasticity, the variance is becoming more and more. It's spread out like a funnel. That is heteroscedasticity. So there must be homoscedasticity because there are some conditions that cause that heteroscedasticity. Especially if you use maybe time series data to do your regression. You know, in time series data, as the time goes on, it's possible the variance or what you are measuring begin to differ much. So some time may affect it. Maybe you are even recording the diagnosis. You know that over time, the prevalence or the disease may vary in population, or maybe even the method of diagnosis may improve over time. You see that the variance may not be the same. So those are the things that cause that type of thing, and some other condition that can cause heteroscedasticity. Now, assumption in conducting multiple linear continuum. Independent error. For any two observations, the residual time should be uncorrelated or independent. The residual time for each, that is, to residual time for different subjects, that is, that error should not correlate. That's what they call autocorrelation. This is sometimes described as a lack of autocorrelation. This assumption is tested by W. Johnson test, which tests for serial correlation between error. The test statistics vary from 0 to, and just leave this one. But this issue is very important in econometry, because the people in business sector that actually have data that have that type of characteristic where there's autocorrelation, the residual correlate one another. They are normally distributed error. This assumes that the residual in the model are random, normally distributed variables with it. Okay, we already said it anyway. If where is related to homoscedasticity, but it's different. You know, normally distributed error. This one corresponds with there's a normal distribution. Homoscedasticity, there should be homogeneity of error. Can you see? So some of those assumptions in using parametric tests, indirectly they are not relevant directly, but indirectly they are applicable not to the y, but the residual, and that is what is happening here. Independence. This assumes that all the values of the outcome variable are independent. Of course, that one also is part of the condition for using parametric tests. Linearity implies that the mean value of the outcome variable for each increment of predictors lie along a straight line. That is, should not be curvilinear. No, sometimes something may follow a quadratic equation. When we say linear regression, we are not saying curvilinear. So the thing must not be curvilinear. That is, it should not reach a state where as maybe the x change further, the other one is no more changing like that. Maybe it's turning back. It's no more, the change is no more linear. And that is what you see in quadratic function. So, in quadratic, something may be going up, just turn down. In quadratic, something may be going down, just turn up. So, it must be linear. Multicollinearity. I want to explain multicollinearity. This exists when there is a strong correlation between two or more predictors in a regression model. it poses a problem only for multiple regression, because simple regression requires only one predictor. Perfect collinearity exists when at least one predictor is a perfect linear combination of order. I think in what we are going to do, maybe we encounter one or two when we run, because we have a lot of data set for this. There are three problems of multicollinearity: untrustworthy, beta, regression coefficient. This is because as collinearity increases, so do the standard error of the beta coefficient. Then it limits the size of R. You see? So it's limiting the size of your, and you know what R means. In fact, in predicting, R to me is the most important, because it's the one that gives you how much variability in the outcome variable that the predictor variable is able to account for. So this is because R is a measure of multiple correlation between predictors and outcome. Yes. Now, here I want to say something. You know, when we run the R, we did the R yesterday. We're going to do it. By the time you do multiple regression, it gives you only one R also. This R now is looking at multiple correlation of all the variables together. It's not just the correlation. You know, if it is linear, and if it is simple regression, which is only one outcome, one exposure, you can say boldly that there is a correlation between the two variables. But when you bring many exposure, that how, which one is it? So it's multiple correlation for all the both outcome and all the predictors together. So when you have multicollinearity, is going to affect it. It will limit the size. You can't tell which predictor variable is important. So because when you have it, you won't know which of this predictor variable that have collinearity is important. I think we go and do the okay, let me entertain question before we go and run. As we are running, we're going to be talking about some of these issues practically. Then there's something I thought I put it here: suppression. When I was talking of why people prefer backward rather than forward, the suppression effect. So there are some variable that will not manifest. It's still related to this multicollinearity. In the presence of another variable, it will not manifest. Or in the absence, it's when the other variable is not there, they show. So that's a suppression effect. So the backward one is said to reduce the effect of suppression effect rather than the forward one. So that is why many people prefer backward to go forward. That's the only thing, suppression effect. So I don't know if there's any question so that we share the data set and start running. Any question? Okay, that's a
I chatted a question.
Yes, I have a question, sir. Okay. I don't understand that. The one where you were saying the multiple collinearity. I didn't get it.
Okay, I will explain. Yes, I saw your. Yes, I saw your. Do you have first test?
The second question I wanted to ask is that the assumptions you were talking about, the assumptions for the multivariable regression. Sorry, that's the multiple regression, I mean.
Yes.
You know, you listed assumptions.
Yes.
Because I like I don't know, I think it just seemed a bit complex. I don't know if there's a way it can still be simplified.
Oh, don't worry, we are
you're answering it.
You know, in fact, what you just raised now is related to the question Prof just chatted now. Say, do you have first test?
Oh, okay.
First test, have to first test the assumption before proceeding with the regression. I think this question was asked last week also. Yes, there are some of them. If you look at it, you see when I talk about the correlation, you have W. Johnson. There are some of them that have tests. They are just funny tests that I didn't want to bother you with. And for some of them, so you don't need the test. It's just for you, to know. Like for example, the multicollinearity is when you run correlation. Can you see now? It's just like the way when you do chi-square before you go and do regression. When you have a lot of what do I call it? Continuous variable, or something you want to use for a variable you want to use for linear multiple regression. It's good to first of all do correlation for them. When you do correlation, you know which one have perfect multicollinearity. If you don't do that, if you are doing it also, you are running it together, you will see it because I have encountered it. You just put in one variable, it didn't appear because there's a multiple collinearity with another variable. Until you remove this other variable, that one yes, you will not see it. It's when you remove the other variable, you see it. You will be able to know that, oh, both of them, and if you go and cross check, that's both of them, the correlation is the same. It's like the same variable. And this one is common when you are dealing with something that have scale, like some of these scale, they say they use to, all those psychiatry they use, all those social science or whatever, all those quality of life, all those scale. There are some of those questions you're asking is the same. You ask this question, you ask this, they are saying the same. So sometimes two variable is actually the same. So when you want to put them in multiple regression, I think I have the same problem with somebody that send his data to one G person. I just analyze. So this person is part 2. After he sent the proposal, the assessor commented, and I said, okay, the candidate can go ahead. I said, okay, well, I can see that like you can do maybe logistic regression to look at the factors. But this person have been issue in his objective. There's nothing like factors. You're looking at factors. He just wanted to know, okay, early anatomy, late anatomy, delay anatomy, and early anatomy. How do they, which one want to compare the duration of labor? So, and also they wanted to measure fetal outcome. About 4 objectives, but none of them talk about factor. You just want to, all those objectives just between delay and early, delay and early, delay and early. So it's going to have 2 groups, delay anatomy, early anatomy. So in fact, it may be difficult for you to even know which one is the main outcome measure, unless it now tells you that the main outcome measure is duration of labor. But he also has, apart from, you want to know the duration of labor between delay and early, you want to know the need for, is it the amount of need for oxytocin, the amount of oxytocin needed, and then you want to know the fetal outcome. So at the end of the day, there's no one, in its objective, you cannot say, okay, this is what is studied, that is studying duration of labor. If you are studying duration of labor, you want to see either early or delay anatomy affected. If you already pinned that you are studying duration of labor, you should know that it's not only early or delay anatomy that affect duration of labor. You cannot bring in other, though you can set down to make it analytical study, you want to know the effect of delay, but you should now do your extensive literature and include other factors that may affect duration of labor. So that by the time you finish, you want to remove the effect of confounder, because if you don't do that, it may give impression. Whenever you see that this delay anatomy, early anatomy is so better than delay anatomy by so amount. So that was the comment the assessor made. Maybe the person didn't understand. So since they say, okay, go on. So the person went on, and at the end of the day, he has not included a lot of all those other factors in his work. You understand? He just went ahead. It was after he had, okay, now say, this is the comment of assessor. I want to do logistics. Can you see? So those are the issues with the analysis. So sometimes And some of the things I had, the duration of labor. You ask for duration in the first, most of the factor, dilatation at the rupture, dilatation 4 minutes before, dilatation 4 hours after, dilatation and this one, a duration of first stage of labor, duration of second stage of labor, total duration. All of them are related. When you correlate them, they correlate. Of course, you expect duration of first days of labor to correlate with total duration. Dilatation at ROM will correlate highly with dilatation at 4 hours after. We correlate with dilatation so it will correlate with the rate of, you also have rate of dilatation for is it per minute now, per 10 minutes or per hour. All those things, they are all related. So when you correlate, when you want to do regression for this person, all those things they put there, there's autocorrelate multicollinearity. Even when you do both linear or logistic, you see multicollinearity. So all of them you can even list about 6 of them. They are saying the same thing. So you can, at the end of the day, it's only one you use. So I was now forced. I did 2 kinds of regression. I don't know how to help. I did linear regression with three variables that you can select out. I do the multiple logistic with only 2 variables because all those other variables there's multicollinearity. So if somebody wanted to
sorry, sir, I have a question, sir.
Okay, sir.
I was thinking, is it because if you put they are doing like this method of first entry, if you force all the variables, of course, from what you are explaining, it means that they will overshadow each other. There will be you only get one.
Exactly.
But if you do it hierarchical, as in using hierarchical method,
it doesn't change anything. The only thing is that if you do it differently, it helps you to dictate it. If you force all of them now, you will now see, if you are very observant, you will see I put in about 6 variables. It's only 4 that is appearing in the result. Do you get it? You know that the other one, 2 have been subsumed by some. So if you now decide to do it hierarchically, you do it one by one. Each of them bring the result. So if you are now adding, you'll be able to know which one swallow which. When you are now reading stepwise, you'll be able to know which one swallow which. I don't know if you understand me now. So in whichever way, either you do it hierarchical or so, that's one just a method for you to dictate how important each of them, and for, at the end of the day, to know which one to use to build your model. Just like for the guy now, I put in a lot of variables. In logistics, only 2 that are available I can do because all those of them are related. Yes, I mean, I put in duration of first stage of labor, duration of total, the duration of second stage of labor is not important so much. Then the total duration of labor is related to is the same thing as duration of first stage of labor, because it's the first stage of labor that contribute most to the timing. So when you are talking of cervical dilatation at rupture of membrane, cervical dilatation 4 minutes, 4 hours after, cervical dilatation at the one and another type. Can you see those 3? They are related now. The people that have advanced cervical dilatation at ROM will more likely have higher dilatation at 4 hours after also. So those are the things. Those variables are related. There is multiple linearity. Dr. Larry, you wanted to say something? Dr. Larry. I thought Dr. Larry wanted. Okay, maybe just. So that's just it. So what Prof is now asking the question, there are a lot of tests, some tests for some of them, which are, yes sir. Go on.
Sorry, so helpful to first do cross tab, so that eventually you know which ones have that are significant before you now put them into the regression model.
Yes, that's good. Yes, right. But even after you have done that also, if 2 variables are doing the same thing, both of them will be significant also when you do the cross tab. If 2 variables they have multiple collinearity, when you do your cross tab, both of them on their own individually will be significant. So eventually all of them will enter. Yes, I'm not. The only thing is that if both of them are not significant, so yes, you are safe, God save us all. So you will not even bother to put them in. But if both of them are significant, you put it in. And if they actually, there's multicollinearity, if one is significant, the other one will be significant because it's the same thing. What they are saying is both those two variables are doing the same thing. They are doing the same work. It's just like you are in a place now, your wife is there in a meeting, and you have a meeting in the concerning maybe your vicinity, and maybe all those estate meetings. You being there, your wife is there, is the same. You get me? It's the same, representing the family. So it's going to be whatever you are consenting for to is what your wife will consent to, because you will have agreed on what your stand. So if both of you are significant, each of you, if one is significant, the other one is significant. So putting both of you now, sometimes is repetition. So that's what just that one just said. Good evening, thank you, sir. Somebody has question. I will do that. See, I should explain the assumption slide and the multicollinearity slide simpler. Okay, I will do that. Yeah, Dr. Bako, welcome.
Thank you, sir.
Pretty late, yes.
Sorry for getting late.
Yeah, no problem. Somebody say, oh, you didn't miss much because somebody said I should repeat, because we actually started from here. We said that the multiple regression, instead of being a straight line, is a plane. If it is that straight line you see, like just straight line, is for simple. That is simple. But when you are now having more than one variable, it will, each of them will form a straight line at an angle to each other. So it will now, if you're having two straight lines that are not on the same line, but at an angle, it will give you a plane figure. Look at this picture I'm showing now. It's two variables. The form of multiple variable. The first one is the one, this line. Airplay, then the other one, the advert. Can you see? If there are, so it gives you a plane figure with 4 sides. Then if there are 3 now, it will give you a plane figure with 6 sides. If there are 4, it give you is it octagon, something like that. So that is just it. So it's when you are dealing with multiple regression now, it's not each of them have its own line, 1, 1, 1, but there's a way they superimpose, they relate together. Now, we now quickly went to the assumption, because when you are doing multiple regression now, so you are not dealing with only one predictor, more than one. There are a lot of issues. How do we talk about the step? Hierarchical, there are 3 ways. Hierarchical step, hierarchical method, we clockwise step. In this case, it's just a situation where you've already have your theory in your mind. You have done literature review or work has been done before. You already know which is the most important variable, the second most important, third most. So you just be putting in another of important from history, from literature. That is hierarchical. That's hierarchy in the sense that you know which one is number 1, which one should be number 2. That is the meaning of hierarchical. First entry, just in a situation where you just don't have that information. You may just, it's more for exploratory analysis. You just put everything in to really know which one come out, still retain his ability. Because anyone that is not a true factor, the statistic will not be significant. If it is you are dealing with this thing, you see that it should not be the p-value. If it's multiple, if it's linear regression, it will not be significant. The p-value will not be significant for under the you're going to see it when we start running it under the coefficient table. It will not be significant. If it is if it is relatively, if it is what am I saying? If it is logistic regression, the odd ratio for that one will not be significant. Can you see? But it has its own drawback. the stepwise method, which I believe is should be the most important one for you to know in some critical situation. The stepwise method here now based on mathematical criterion. What I mean by mathematical criterion is good also to have done simple regression for each of them. When you have done simple regression, you will know if it's linear regression, you will be able to know which one has the biggest R square, the big R square for you to include first. So is the one that has the big R square, apart from looking at the level of significance, but you look at if the significance also, the most important is the R square. You look at the R square and the F ratio, the one you think contribute most. You'll be able to now guide you how you do it step by step. So in forward step now, you begin to load in the most important one based on your R square. Then you load in the next one to see what improvement has he made. Try another one also, because for the fact that somebody still another one has higher R square than another one doesn't mean that it's more important than the other one. So when you load in the first most important, if you put in another one that is the next, it may not increase the R square, because the R square will not be don't worry, let's go around, because don't let us talk much here. When we run into, we go to see, because I'm going to demonstrate with somebody's data. You see it. That data I cannot share with people with somebody's data unless the person give me permission. It's a lady that did part 2 pediatrics, but I can run it. I cannot share it. That's why I didn't share the data. So before I can for me to even extract those variables out and share and be using it, I have to get a permission. But I can run it for you to see. So it's not part of what I give you, because it has the classical what we are looking for. But however, we have other data also that will show us, which I have shared with you. So most of these things, in the backward one, you load everything, begin to remove. Begin to remove the one that is least important. We'll do it because it's better done than just be explaining to the blue moon. So the assumption for you doing all these things for running multiple regression, that was the question you could say I should repeat. Now, Prof send a question, is there anything, some of them have tests to carry out. I even may mention some of them here. The variable type, all predictor variable must be quantitative or categorical, which I have explained. All predictor must, then the outcome must be quantitative, continuous, and unbounded. In linear regression, the outcome is continuous or unbounded. Unbounded means that it doesn't have, it's not something like maybe percentage. Look at you don't have boundary for the range of value is not limited. Though actually in life, somehow there is something that doesn't have limited range of value, but this one now, when like height, now we know that the range of height of people we can study, but we still have people that have extreme value. It's not bounded. But if you are measuring something in percentage now, maybe if it's proportion, it cannot be less than 0%, cannot be greater than 100%. Can you see it's bounded? Or this is on Likert scale 1 to 5, or Likert 1 to 10, it's bounded. So for continuous value, it's not bounded. You will see what differentiates linear regression for logistic is the outcome. The outcome variable for linear regression is continuous. The other one is categorical. But for all of them, the exposure variable is the same. So look at the first part of the sentence. All predictor variable must be quantitative or categorical with co-category. So even in logistic regression, the predictor variable can be continuous, can be categorical, but it must have 2 categories. It can be, that is 1 or 2, 0, 1 or 0. Though the only difference for this linear regression now, the categorical variable must be input to that's why you put the 1 0, 1 0. But for logistic, you can still have ordinal variable being there. It may not necessarily be 1 or 0. So for linear regression now, the continuous variable, the predictor, either continuous or categorical. If it's categorical, you must create a dummy. That will be 1, 0. I think that one is solved, right? Non-zero variance. What it means that the value must vary, the value of the outcome. You cannot have, like for example, you want to, this one is a factor, and all of them have the same value. For example, since we say that we can use maybe diabetes, yes or no, as an exposure, as a predictor. So all of them, no diabetes. No. You cannot, it's not more, of course, you know that it's not a variable again. Because for something to be a variable, the meaning of variable is something that has different value, assume different value. So if it's only one value, it's a constant there in that of study. Just like somebody that you are studying, went to study women at antenatal clinic. You cannot be talking, sex is not a variable again because it's a constant. Because eventually, if you enter the cell, all of them will be female. So, non-zero variance, that is, there must be variance. You cannot use anything that, you know, some people, when they do a study, they collect value of a particular variable and there's no, they still want to put the table. You don't need to put it on the table. You can just say it in your methodology, all of them are female, simple. Or none of them, in the study, nobody smoke. It's better to go and have a table where you say, smoking yes or no. No, 100%. Yes, 0. That's absolute nonsense. So it's just wasting space. So no zero variance. That's what this means. You don't include that type of that of variable. There are no perfect multicollinearity. That you will not be perfect multicollinearity. I've explained multicollinearity when you are having 2 or more variables. Perfectly, their correlation is 1. Perfect. They correlate perfectly. If that shows that they are 1, it's the same. It's the same thing. Just like what we say, husband and wife. If they have the same opinion concerning something, if you ask the husband, he says tell you the same thing. You ask the wife, if you go for a meeting, is the same stand. That is so. The husband and wife should not be said as, or it should be regarded as one family and say this is also Jeffrey family. This is what they say. You won't say Jeffrey wife say this, and they are saying the same thing. Jeffrey say this. So that's multicollinearity. So you cannot feed both of them as different variables. They are serving as one. So that is what it means. No perfect multicollinearity. Then predictors are uncorrelated with external variables. This one I said that is very, very dicey. What it means is that you may have a predictor in your model that there is a variable that is not in the model that it perfectly correlates with it. You get the picture now. That shows that it's possible that is the one that is confounding. The predictor you are having here may be, the correlation you are seeing may not even be, maybe a spurious. It may be because of the other one that is outside. And that is why this one is difficult to detect. You know, there's no test you do for this one. That's why not everything has tests you do. Like this, no perfect, even all these things we are saying, number 1, 2, 3, 4 now. There's no test. The multicollinearity is during correlation. When you do correlation, you'll be able to know which one correlate. Otherwise, when you are running the regression, one will disappear, you will not see it. You'll be looking for it. So if you go and correlate, you will be able to know which one. Or when you are doing it step by step, you know which one disappear at the site of which you know that both of them correlate perfectly. So some of them is in the process of you get to know them. Then this external variable, when you do your literature review very well, it will help you to know many factors. So that is the essence of this type of analysis, to remove confounders. So that you will not say a particular variable, yes, is a factor, whereas it's another variable that is confounding, and that variable is not even included in your study. So, but this one is difficult to detect anyway. Difficult to detect. Then homoscedasticity. This one just talk about there should be homogeneity of residual variance. That's the meaning of, if you remember homogeneity of variance in one of the conditions for using parametric test, that is the variance for different levels. Like if you are trying to do t-test now, between these two groups, their variance should not differ. Even if there are three groups, their variance should be the same. Even though their mean may be different. That's what you are testing anyway. But the variance, that is homogeneity of it. But this one is not is the residual. We have talked about residual yesterday. That is the difference between the predicted y and the observed y. The outcome variable, the predicted and the error. That is the residual. So the residual must be the same across the different values of x. This is what is shown in the picture now. So homogeneity, if you look at this one, the one that is homogeneity of variance, if you draw the line, so you will see that across the length, the width of the extent of the error does not change. Can you see? It's like as if they are walking in a tube. But look at this heteroscedasticity. It's like a funnel. As the value of s increases, the error begins to increase. There are many factors that can contribute to that. Outliers, if you have outlier, can contribute. If you are using what do I call it, time series data, or data that you collect over time, yes, because time has a way of changing data. Whereas if you are collecting data in the hospital now, the diagnosis method of diagnosis may improve over time. So it will change the variability of the results. Something may happen over time. So summer, usually happen in that type of data. Then, and many other factors also that can cause heteroscedasticity. So it's now the residual should be the same. The distance, the variance of the residual from the regression line should be the same across the different levels. So this plot you are seeing now, the x-axis is the what do I call it? Is the exposure. While the y-axis is not the outcome, is the residual, the error in predicting the outcome. The error. Then independent error. The error should not, this residual still should not correlate. That is for different subjects, should not correlate. Apart from, should not be, should not correlate. That's what they call auto correlation. And there is a test they call W. Johnson test. But when you are running this also, there is a way the computer will even bring it for you also, W. Johnson test. So he's saying that we test for serial correlation between error. The test persistence vary from 0 to 4 with value 2 mean that the residual are uncorrelated. A value greater than 2 indicate negative correlation between adjacent residual, whereas a value below 2 indicate positive correlation. The value depends on the number of predictors in the model. This one is common with in econometry, because they are the ones that usually have data that have the error that have autocorrelation by the nature of their own their own data. Let me give an example. When you say you are talking of the rate of profit, in a business, you are measuring the profit over years. You know that it's difficult to put that type of profit on a linear scale, because if you say the profit, you start a business this year, the profit is 20, maybe 5%. Next year, the profit may increase to 20%. But you know that that past 5% also, the previous year is contributing to the 20% also. So because the way it's about economy of scale, it's just like it's the same thing. Like when I say, okay, people should help me register for this thing. register. If you register, if you are playing this thing, some people will say, I want to be part of this thing. So you see, me, I value you. Even you, I can even allow you to come and attend the training free, then than you not registering. So if you register, I prefer it. You even than you say you are not okay. If it's okay, come and attend this training free. Me, I value it more than you not registering. In the sense that the registering will give you opportunity of having other people, maybe when they see you are benefiting from it, they may get it. So that is how they work in business. That is why this autocorrelation, most of their own scale is not on linear because it's more like a geometric. So they usually have autocorrelation. That is why it's a problem in econometric. But we don't usually have that problem much in medicine, in biological science, because it has nothing to do with all this multi-level stuff, refining this one, refine this one. Because when we are talking of economy issue, it starts today before you begin to spread. The profit begin to either profit or loss, whatever they're measuring, changes in the geometric scale. So it usually produces this autocorrelation. Now, because somehow one affect the other. Normally distributed error. The error should be, we are talking of the error all the time now. Most of the things that are assumptions that apply to the variable generally, when we talk about using parametric test, is applied not to that variable, it's applied to the residual in regression. Can you see? Normally distributed error, the residual should be normally distributed. This assume that this one has test, so there are many, because some of the diff. I didn't just want to tap with it because some of it is just for you to know that they exist, because in interpreting your results, once you are able to establish that the model is fit, it doesn't affect the interpretation of the result. It's just to be able to show that the model is okay. So normally distributed error, this assumes that the residual, the model are random, normally distributed variable with a mean of 0. Independence, this assumes that all the value of the outcome vary independent. If you look at this number 7 and number 7, even all of them, number 6, 7, 8, it's the same thing you see in assumption for using parametric test, but in a different way. Independent. Instead of talking about independent, okay, this was an independent. Yeah, it's the same independent, but you have independent error. It's applying to the residual. Normally distributed is applied to the residual. Some of them apply to the residual instead of applying to the data set, the Y itself. Linearity implies that the mean value of the outcome variable of each increment of the is linear. So this one, that's what we call a linear regression. That is, if there's a point where as one variable increases, the other one does not change in the linear fashion, then it violates linear regression. Of course, there is provision for that, curvilinear. That one's another, because you have to bring in the quadratic function in the equation. When you know y is equal to a plus bs, you will have to add plus bs squared, b2s squared, b1s plus b2s squared. There must be a quadratic function. It's no more a linear. So if it is linear, the linearity must be there. If by the time you see that the function is not linear, it's not appropriate, that particular variable is not appropriate for linear regression. Yes, the last one, multicollinearity, we have discussed it just to throw more light. I've already said it, when two variables perfectly correlate. So it produces unworthy, untrustworthy regression coefficient. It limits the size of the R square, R correlation. The R you see in multiple regression is the combined correlation of all the variables there. It's not just between one or two, two of them. You know when you run your bivariate correlation, it pairs them and give you, even if you load about 5, it will pair them in different way. But this one, when you put in many variables, even 4 variables to the linear regression, so the outcome will be number 5. The R is the correlation of all of them together, put in one. So if there's multiple collinearity, it will affect the limit the size of the correlation. So we can't tell which predictor is important. Yes, of course, this one is very straightforward. So I think that's what I just said. I don't know if there's any. Let's just go straight. If there's any other question, let's just go straight to practical. Some of them will be ironing them out. We'll be seeing them face to face. I think it has given some explanation, Dr. Iguilo. Okay.
Yes, sir. Thank you, sir.
Yeah. So who will share with us? We have some data set. Let's first of all, there's one data set on death rate. What did you share? Death rate. Let's use it to start. Death rate. Oh, you don't have it? Oh, I should share my own.
We have it.
Yeah, somebody should share. Let me allow you to share. Yes, you can. Anybody I want to share can share now. Death rate. Okay, let me share my own since. Can you see it? Can you see the data set?
Yes, we can, sir.
Yes.
Yes,
So
sir.
we have,
Yes, sir. We can see.
yeah, we have 5 variables there. And if you go to data editor window for you to understand the variable, if I was telling you now, it's very
0, 1 to Q 5.
Yes, I was looking for the other one. Yes, I want to look at the labeling of those variables so that you understand. The first one is death rate per 1,000 residents. The second one is doctors availability per 100,000 residents. The third is
Hospital availability.
per 100,000 residents. The fourth is annual per capita income in thousands of dollars, and the population density per square mile.
Per square mile.
Yes, the outcome variable is the death rate per 1,000 residents. That's the outcome. All those other 4, they are exposure variables. So let's just try to practicalize what we have done, we have learned. But we may first of all, let's do simple regression for each of them to see their R square. It gives us a mental picture of who, each contribution of each of them. Okay, regression. So the death rate is a dependent variable. Let's try hospital availability. Just simple regression.
The first one.
Yes. I don't know. Let me share the outcome and output. Can we see the output now?
Yeah. Yes, yes.
Yes, you can see. So let's just let's look at the outcome. Don't bother yourself about all those coefficients. We have already explained all those and over everything yesterday. Let's just look at the R square. We want to know the relative importance of each of them. If you look at the R square now, what is the R square here is
1.013.
Yeah,
1.3%.
Yeah, 1.3%. So what it's telling you is that the This
hospital availability.
Doctors availability contribute 1.3% to death rate. So now, one thing I want us to look at, because we didn't have time to discuss it yesterday. I don't know if normally, if you do correlation, for maybe we should first of all even run correlation so that you see the way they correlate. It makes sense. Let me run the correlation. Let's do correlation matrix. Because you know correlation is part of regression. So you cannot push correlation away. Let's just move all of them now to see how they all correlate. You can see the matrix now. You can see the matrix. You will know that the way correlation goes along the diagonal, that's where each of them correlate. The way we list them, death rate, doctor availability, hospital availability, annual per capita income, population density, as it lists it vertically, it also lists it horizontally. And now, along the diagonal, this is where death rate correlates with death rate to be 1. This second one, doctor availability correlates with doctor availability to be 1. Hospital availability correlates with hospital availability to be 1. Annual per capita income correlates with annual capita to be 1. Then the last one, population density correlates with population density to be 1. So what the real correlation you are looking at is off the diagonal. And what you have on one side is mirror image of the other one. So it's just one you just choose. It's the computer is, because it's not human being. That's the way you program it. That's the best way you can give it for us. If it is human being and not, okay, no, this one has been there before. No, just list only one side. So it's just for you to pick, just consider only one side of it. So like now, if you look at doctor availability and death rate, is, can you see the correlation is 0.11. So that is what we see in the regression. Can you see? Can you see it? Please, I want you to respond. That's the answer we see in the regression. Yes, when we look at the R in the regression, is 0.116. Is the R we saw in the regression. So, so you can look at it here. Is the, that's what we are seeing here. No. So now, if you look at this one, correlation of hospital availability and death rate is 0.11. But even from their correlation, you will know, to be sincere with you, which one will contribute more in the R square. Look at annual per capita income. The correlation is negative correlation. This data says is negative correlation. Of course, you expect that because the more the money capital, the less the debt. Yes, I mean, if you is speaking, can you see now? Normally, you expect that the doctor availability and death rate should be negative correlation. It's positive. So you can have many doctors, and if they are concentrated in one place, it doesn't really help. Yes, I mean, the same thing with hospital availability. You expect them to correlate negatively with death rate, but it's positive. Don't look at the one that correlate negatively with death rate, which is good. Annual per capita and population density. No, even the population density, we expect that if the population density increases, death rate should increase, but it's opposite. But the one that makes sense here is annual per capita income is in opposite direction with death rate. Yes. But if you
excuse me, sir.
Yes, sir.
Listen, I have been thinking of that population density issue since the other day.
Okay.
I have a feeling that maybe the explanation could be this.
Okay.
That when the population is dense, you can have more health facilities, more doctors, and all that. And these factors could contribute to reduction in death rate. For instance, in urban centers where there are so many people, we have more healthcare providers there, we have more health facilities.
Yes, you are right, sir. That's the explanation. That should be the explanation, because in the urban, we usually have the population that's in the urban, and most of the health, the doctors concentrate there. The doctor concentrate there, the hospital concentrate there, everything, the good service concentrate there. And that is why we are seeing the result in the opposite direction now. Can you see? That's what brought doctor availability to be it's not in the right direction. Hospital availability is not in the right direction. Population density is not in the right direction. What we are just saying now can explain all those things. So the only one that makes sense is the per capita income.
Per capita.
Yes, because it's in opposite direction to that is negative correlation with death rate. But what you should look at here now is the value of the correlation. You see the population density is the one that have the highest value, followed by per capita income. Can you see? So then followed by the doctor availability, the hospital availability. What I want us to look at is that when we run, look at
hello.
Okay.
Hello.
Yes, sir.
Can you hear me?
Yes, sir.
What is the significance of this two-tail? Because it seems you are not using it at all.
Two-tail.
Significant two-tail.
That what you have.
You are not looking at it at all. So
I've already. This is a when you see significant means p-value there. When what the SPSS called significant is a p-value. We already discussed that the p-value.
Okay, so this is p-value.
Yes, now just say two-tail p-value.
So this is p-value. This significant two-tail is p-value.
Yes.
Okay, that's why. Okay. Then it's
I think
clear.
we already explained the difference between 1K and 2K before. So and we already said that even the significant is not useful because yes, it's affected by the sample size. We don't usually use it to
useful here.
Yeah, we don't use to interpret correlation because it's affected by sample size. If sample size is very large, a small correlation will be significant. If sample size is very small, a big correlation may not be. Can you see now?
Can you say that again? You said if sample size is what?
It's very large sample size. A very small correlation may be significant. And if the sample size is very small, a big correlation may not be significant. Yes, sir, now. So that is why we have this the interpretation of correlation that if it is less than 0.2 is negligible. You know, from 0.2 to something like 0.5, that is we call it weak correlation. From 0.5 to around 0.75 or 0.8, moderate. From 0.8 to 0.9, you say strong. From 0.9, strong. 1 is perfect correlation. We have already discussed it. That's how to interpret it. We don't use the p-value to interpret it. So what I just want you to look at that negative, the one that have negative now. This annual per capita income and population density. When we do the regression with it, you will see what will happen. You will not see the negative with the correlation. It will not show it there. The negative will show with the regression coefficient B. So let's continue the regression now.
So the annual per capita income and the population density I'm seeing here. It's just, is that minus or 0.129?
It's minus, both of them minus 0.172 and minus 0.278. Which one?
I think, wait, I'm looking at annual per capita income versus the population density. Okay, it's death rate. Oh, because you were saying population density.
I'm just looking at, yes, I know that all of them correlate with one another, but I am not bothering much. Okay, is there anyone that perfectly correlates? Let's see. Which one is 1? Is there any of the 4 things that perfectly correlate? There's no one. No, that is how to know perfect collinearity.
There's none. There's none that is perfectly correct.
There's one data we looked at.
There's none.
Yes, there's one. Don't worry. We'll do it. I think it should be that lady's There's one. We know we have many data here. Don't worry. Let's quickly rush through. We have many data on this thing. So let's just quickly work this. Let's do the correlation now, the regression now. Okay. let's look at annual per capita income now. You see. Can you see the results? Can you see, you see the correlation now. It's 0 minus 0.172, but it just say 1.72 here. It didn't put the minus.
That's very sure.
I thought I'm already in analysis mode that it's just.
No.
Okay.
Can you see?
Can you see?
Not yet. Yeah.
Okay. Now look at it. Look at the R. The correlation with annual per capita income is negative correlation, minus 0.172. But what you just see is 0.172. Because when you are running the regression, it doesn't give you, the R does not give you the sign of the direction here. But this, just look at the R square. Maybe the reason that they are interested in the R square. It's not even the R. The correlation is the R square. Can you see the R square is 3% now? Can you see?
3%.
3%. Now, if you remember, the doctor availability is 1.5%. Now, look at the coefficient. You see that the coefficient is minus the B.
0.2.
Exactly. So that is where it's telling you that as the annual per capita income increases, death rate in opposite direction. So exactly, is the coefficient that will give you the direction, the sign of the either in minus or plus. So maybe it increases or decreases. Does it make sense? But if you run it as correlation, you will see the sign in the correlation. But when you run it as regression, the arrow will not show you the sign. It is the sign. Yeah, it is the B, the regression.
So is that the slope?
Yes, that is the slope. Now look at the B.
Okay.
The constant in the 11.18 is B0. Why this one is B1?
B1.
Now look at it now. Constant 11 point. That is the B, the intercept.
Okay. That's when X is 0. Okay.
So annual per capita income. This is the coefficient for annual per capita income.
So that's why it's in the negative.
0.2.
Okay.
Because it's in the opposite direction. Yes.
Opposite direction. Thank you, sir.
But the constant being negative has nothing to do with direction. The constant being negative. If you remember the one we did yesterday, the constant is negative. When we look at the height and the preliminary death rate, the intercept is 0 minus 82 point something. You remember? That's nothing to do with the direction of the relationship. Yes, I mean, no, that one it just means.
I was talking about the slope, sir.
Yes,
okay.
Intercept. It just that one just means that the graph cross the y-axis down.
Down below.
Yes.
Yeah.
But here now, the graph cross the y-axis up, but the slope is negative here. Can you see? I don't know if you can be, some of those things we discussed now, you can see the way it goes here. So the slope is negative in the sense that as the per capita income increases, the death rate decreases. The slope, and this negative here means that the slope is negative. Then this positive constant means that intercept is positive, above 0, crosses the y-axis. Now,
yes, sir.
Yeah. So let's the same thing. Okay, let me just do that one by one. So let's look at the last one, population density. So can you see, or should I share again?
It's okay.
Well, now let me share again. So can you see? The last one, if you look at it now, it the R square is 7.7. Can you see now? 7.7%.
7.7%.
This is the one that has the highest. And if you look at it also, because it's moving in opposite direction, you can see the slope is negative. Can you see? The B. The slope is negative and the constant is positive. So now, from here now, if you want to do multiple regression now, all you need to do, okay, let's start with the most important one. So let's start with the most important one. Yeah, the most important is even already there. Let's just correlate No, regression, linear. Now, this population density, that's the highest one. We now say next, we want to do stepwise. Can you see? You say next, you now load in, the next one is annual per capita income. Let's see what it has, the combination of their this thing.
Contribution.
Can you see the results? Or should I reshare?
It's
You can
okay.
see it, sir.
It's okay. It's okay. We can see it.
You can see the. Can you see now? You under the model now. If you look at the first table that usually come out, you see that in the model you are putting two things in the model: population density, then annual per capita income. The dependent variable is outside because it's the independent variable that you are using to build the model. And you see now, the outcome variable is usually outside the model. It's not. That's what you are building model for. So as you are adding now, if you are adding, so there are two things inside the model now. Now, when you look at it, because we did this stepwise, this R is for the first one, which is the population density. Now this one is the for both population density,
and per capita.
And per capita. So it can increase the something to 9.6%.
6%.
Yes, I mean now. So if you look at, the other one was 3%, and this one 7.7%. Mathematically, 7.7 plus 3% will give you 10.7, right? You cannot have it mathematically like that because there will be some area where they overlap, also they confront for one another. What I mean is that you may see some of this per capita income may be due to density, population density, or some of the effect of the population may be due to per capita income. Area where they overlap, that is what has removed from it. So that is why the addition R square is not mathematical addition of their separate R square. So it's when you run it together, this is a combination. So both of them contribute to 9.6%. Does it make sense now?
Yes.
Yes, sir.
So both of them contribute to 9%. And you now see, you see the beta.
Okay.
In dollars, then look at the coefficient. So you also have the coefficient for, can you see now? No, this is second model now. Can you see now? It will have coefficient, but for both of them. No, look at this, the second model now. This model, look at the constant. The constant has shifted.
Can you scroll?
Yes, the constant has shifted. You see, look at the coefficient for population density now. It has changed, and the coefficient for annual per capita income in 1,000. Can you see? But it's still showing that both of them, they are in opposite direction. Yes, I mean now, to death rate. That's what it's showing. So now,
why do we have excluded variables?
Why do you have
excluded variable just below that coefficient table?
Dependent. No, it's just telling you that excluded variable. That is any variable excluded. There's no variable excluded. Yeah.
Please scroll down, sir. Scroll down, sir. There's a variable excluded.
Okay.
Annual per capita income in dollars was excluded.
Annual per capita income in dollars. Is it that annual per capita income in dollars? Okay.
He said excluded, and if you look at the side, it has collinearity
statistics.
Statistics, yes.
Where? Okay, was it because the other time I confess for annual per capita because before I remove it, or it may be maybe there is somehow collinearity between what and what now. I want to look at it. That rate predictor variable where unless what I will do now, I will remove this thing, I will now reload it again to start to see what really happened. But it's possible it may be trying to explain to us the overlap between both of them. Yes, and I know that if you look at the R square has reduced, somehow there will be something that is common between both of them. I don't know you
Yes.
understand. So just wait. Let me go back to that analysis. There are some of those things you get to even observe if you are running them. Okay.
Death rate.
Mm-hmm. And population
And
density.
Population density.
And population density is the first one.
Okay.
Yes, I wanted to ask if we are doing first entry, you're going to add all of them into that first one,
Yes,
Abi.
we can
All
do
of them
that.
will enter. You're not going to be doing that next. Everything will just enter that first page.
Yes.
First box.
Yes,
Okay.
that's
Thank
first
you.
entry. You
Yes.
push them into
Okay.
that box one
First.
by one
Okay.
at
Okay.
the same
Thank you.
time. Yeah.
Okay.
I'm coming. I will run it now. Yes. So you can see the result now. Well, I think it's because of, to me, it may, Dr. Adesina, it may be maybe somehow the part that, you know, there's a correlation between both of them also.
Yes.
The population
Okay.
density,
Okay.
that effect,
Yes.
it has the what
Yes.
has to, that
Yes.
is why the thing did not add together. Yes, I mean now. So
Yes.
there's a portion of that where they maybe correlate. Maybe that's what it has removed. Yes, I mean now.
Okay.
And if you look at the annual capital income, is the second one. Okay, let's redo it now. Let's put annual capital income as the first. Let's see what we do.
As the first. Okay, let's see what
as
we
the
get.
first, and let's see what it gives us. So we put annual per capita income, next population density. Let's see. Can you see? Can you see? In that same population density,
it excluded population density this time.
So what is, if you look at it now, if you see, let's see the percentage. The percentage is still the same. You understand me now? Can you see? The total percentage.
Yes.
But if you want to build your model, it makes sense to first of all put the one that will give you the highest. Can you see? Yes, to give you, because from this one and the population density is more important than the per capita income. You put it first.
Yes.
So let's continue. Let me redo it and continue so that we put the other one. So after we finish building it, we can go and force all of them to see the way it goes.
As you are doing this, can I also ask another question?
You can ask.
You know, there's constant.
Yes.
There's and this SPSS or most of this data analysis software, they will also give you p-value for constant. What is the significance of that p-value?
Yes, yes. That one, you know what we are, okay, yes. That one, you know that the value of y when x is equal to 0 is the constant. Are we following?
Yes. Yes, I'm following.
Yes, that is what is telling you that even if x is not there, the y has an appreciable significant value.
Okay, appreciable significant value. Okay,
exactly. Even when that particular factor you are talking is
not there.
There is
so it's an appreciable.
Exactly.
Appreciable significant value. Thank you.
If you still look at it now, you will expect this one to have all the significant value, because if you look at the contribution, it's still 9.something%.
Yes.
You will even be surprised if the p-value constant is not significant. It will be significant because it's still telling you that a lot of things that this one cannot even account for, they have it. The value of y, they are there. So it is when your R square is so big that maybe the model you have built is so has only account for most of that the constant may not be significant. I don't know if you understand me now.
Yes, I understand, sir.
Yeah.
Thank you, sir.
Welcome. If you look at it, you will see that even the T for the constant is bigger than the all of them. You see.
Yes,
Even
yes,
if you
yes.
see the T for the constant, so it's bigger.
Yes.
So it's telling you that the chunk of the what is to be explained is still there. That is not explained.
It's by the constant.
Yes, it's still there. That's the value of y when x is 0. So
Okay.
it's just a pointer to say that there are a lot of factors you have not accounted for by what you have just done. Okay, I have done the third one. Look at it. Look at it. What is the something? It has increased to, let's see.
The R square.
30.2.
It has increased to 13.2.
Yes. So if we let's add the last one. Which is hospital availability. So the total is 40.4. Can you see?
Wow. Okay.
So all these factors they accounted for here account for 40.4. So we still have 85.6%
unaccounted for.
Exactly. And that one will still be under the constant. Yes, yeah. I mean, it will still be under the constant because you cannot, if you look at it and look at the T for the constant, it's still there. It's bigger than for all this other one. So that's just it. Now, let's share there's another something, systolic blood pressure. We have some, we didn't even explore that one last week. Systolic blood pressure. Somebody should share.
Scroll down.
Sir? Somebody is asking, any question? Any question? Somebody is talking. Can somebody share this?
Go ahead, sir.
Systolic blood pressure. I want the AC and what? So nobody want to share, okay?
I can use my own.
No problem. Systolic blood pressure is part of what and even the pH of where. I think that systolic blood pressure has about
systolic blood pressure.
Yes, I'm looking for it. Okay, I've seen it.
It's very close to the Zoom. Zoom,
yeah,
yes.
I've seen it, yes.
Okay.
Okay, there are 3 variables here. You see the systolic blood pressure, the age, and weight. Can you see? So the systolic blood pressure is the outcome. So the exposure.
No, we are not seeing it, sir. We are not seeing it, sir.
It's not yet shared.
It's not showing. We still have the death rate.
Don't worry.
We still have the death rate data.
Okay, sorry, I will share it. I will share it now. Sorry. Can you see it now?
Yes, yes, we can see it now.
Yes,
systolic blood pressure.
Yes, I will look at the 3 variables: systolic blood pressure, age in years, and
weight in kilograms.
So the systolic blood pressure is the outcome variable, the exposure at the age and weight. Let's see. Let's first of all correlate to see the way they look like. Let me share the output. Can you see the output? Can you see the output?
Yes, we can see it now. We can see it.
So you see the age correlates with systolic blood pressure is 0.979.
979. Very strong correlation.
With weight is 0.971.
Very strong.
Yes.
Also very strong.
But if you see where weight and age correlate, also 0.946. Now, let's quickly look at, let's start with age, with systolic blood pressure. You know, sometimes this data set now,
Excuse me, sir.
Yes, sir.
This very high correlation between weight and systolic blood pressure, could that be seen as cold linearity?
Well, I don't think so because if it is 1 now, it will be a perfect one.
Okay.
It's not a
Okay, sir.
perfect culinarity. If it's 1.
Okay.
Mm.
Okay.
Okay, let's do it and see. So regression. So systolic blood pressure. Let's start with age. Let's see what it gives us. I don't know. Are you see the results?
Yeah.
Yes.
You see, the
Yes.
R square is 95.8.
95.8.
Thank you. So
Okay, let's see the coefficient.
look at it. Look at the coefficient.
Coefficient is positive
1.4. Yeah.
But the constant is also very high.
Yes.
1.46.
Yes. And the high. What do you mean by the constant is very high? What do you mean?
No, I want to.
You know, the absolute value of the constant and the regression curve has nothing. The absolute value nothing, just to fit into equation.
Into equation, yes.
So I thought you are looking at the
t-test. T-test, yes, that's what is important.
Yes, if it is t-test now, if you look at it now, the
but it's less than the age.
You know, the bulk of it already, exactly, the age has already
explained by age.
Exactly.
Yes.
Yes. But the remaining one is still significant. So now let's do it for weight alone also. So can you see? So 94, the same thing.
94.
But you will see, yeah, but if you now come and see the significant, the constant is not significant.
Constant is no more significant here. Yes.
Can you see now?
Okay.
So now let's now combine the two.
Excuse wait. Before we combine the two.
Okay.
Excuse me, let's explain this. This constant that is not significant here.
Yeah.
The constant that is not significant here. The meaning will be that weight is explaining the whole of our variable of systolic blood pressure here. Is that the meaning?
Well, I think so. Yes, I think the reason is that, okay, for us to be able to explain it very well, let's go and run the two. You'll see what will happen.
Yes, no, I want us to just put a meaning to this first before we, so that we'll now compare what we get when we do the two.
So what it means is that that significant with age, that time, the constant was insignificant.
Yes.
Maybe telling us that a lot of things, you know, age is a big confounder. You know that?
Yes.
In many things, you know, all those demographic variables, they are the confounders. That is why we usually take them to analyze for them. You get the picture now. So
yes,
it may be saying that, okay, even though age gives a lot of the value there are some things sounding for it, but this weight now has contributed a lot. So what remains is not important.
It's not important again. Yes, that's
so
what.
It may be a factor that weight is even more important than age.
Than it, yes. So okay, so let's do it together now, and let's see.
Yes.
Let's do it together so that. Oh, it's funny.
Okay, let's even make let's make age the second one self. Yeah.
What's our R square here?
I'll come. Yeah. Let me scroll. Can you see it? Look at the R square is 97.7. If you look at it,
that's the R square. Okay, for weight is 97.1. No, 94.2 for
yes,
for
all of them, but both of
weight
them.
alone.
Yes, it's
No, for both of them is
alone.
for both of them is 97.7.
Yes. So
For
what
both
is
of them,
telling us that
97.7.
a lot of the contribution you see in age is because of the weight. It's the weight that is contributing to the hypertension. It's not actually the age.
Age.
I don't know if you understand me now.
Yes, sir.
You know,
but can we see the coefficient?
Look at the coefficient.
Okay, I agree with you, sir.
Yeah. So if you look at it, so both of them are still significant. So if you look at it, age and weight are
yes,
still,
both of them are significant.
but what is telling you, of course, now you cannot have.
But weight is contributing the most.
Yes, it's contributing the most. Yes, it's contributing the most. The most. Yeah. Even though don't just neglect because this is giving impression that well, it may be difficult to say, but from what we have seen with the constant, I think weight is contributing more because you cannot use significant to judge it. If you look at the significant, it's giving the impression that the age is more significant, but that's not the issue. Though from the significance of the constant and for the weight, the constant is not significant. It shows that weight is a stronger factor than age. Are we following?
Yes.
So for the fact when you see that when you run something, one is 90, one is 90, you know that there's a confounder. They are confounder because there's no way there will be overlap.
There's an overlap. There's an overlap
here. So you cannot have more than 100%. You cannot have 19 plus 90 to give you 80%. So it shows overlap. Yes, I mean it shows overlap. But if let's say another something like exercise is there now, it will explain some other thing. Because somebody also that if you are becoming older and you are doing exercise, you are not likely to have age weight. Are we together? Okay, let's look. There's another data set.
Yes. But something is funny here. Yeah. Something is funny here. When you look at weight and the constant, the significance for constant with weight and constant alone is not significant. But when you look at age, weight, and the constant, the constant, the p-value for the constant is still significant.
Okay. Maybe it's the effect of the age still. It's the effect of that age.
Is it age?
Yes, now because it was it was the age that was actually that, you know, when we did the age also, this constant was significant.
Yes. Yes, the constant was significant, yes, with the age alone.
So actually, if let's say we are able to, you know, there are other factors that are being lost here. If let's say they have height now, BMI will have been the better one to assess.
Better, yes.
Yes, and because sometimes the people that are tall, averagely will have more weight than people that are short. Yes, I'm now. And being is the BMI. If somebody has more weight and is tall, it's not a risk like somebody that is short that has even less weight, because it's the BMI that matters. So that is, you know, all those things. The statistic cannot answer your question. You have to put in a lot of things. If let's say in a data set that you have done a lot of literature review, all those factors that have been incriminated, you have put them in. You'll be able to see. Don't worry. Let's just look at this thing. We are going back. The last one will be on that lady's data. It's quite interesting, and I will show you the way you show the result also. It's quite interesting. It's only that I cannot share the data with you, but I will run the data. It's quite interesting. You know, sometimes it's difficult to get the interesting data. You understand me now? So interesting data that gives you the real issue, you'll be able to see. Sometimes when you are running analysis like this one, you yourself, you'll be excited. The type of revelation that begin to come to you. You begin to see, with this thing, all those things they are talking of risk factor of this thing, they are true. I've handled a lot of data. Let me tell you something. It's not life. People, if you do exercise, the risk is lower. I've seen it like face to face in data like this. You that do exercise, the risk is less. All those, because those are the studies that have been done, yes, and by experts, which has been validated over and over and over and over. Okay, let's try and share. Let me share this one. There's one on pH. No, I just put it there. I didn't even run it. pH and a well. Let me look for the data. pH and well water. Yes.
Only 2 variables.
Okay, it's only 2 variables. Maybe just discard it. Let me share that. Let me look for that lady. Let me look for that lady's work. I will share with you now. Let me open this. So this is the data set. Can you see it? Can you see the data?
Okay. Yes.
And let me share with you the result also, so that you can be seeing it, because we don't have much time. I will share the result with you also, the way I tabulated the result, because so that when you are seeing the result as we are running it, you see the way it came. Just a minute. Yeah. Okay. I think we can. So please, can you see the result you are seeing here? Yes. I just want to show you the result before we run the data.
Okay.
So what this person was looking for is looking at the predictor of peak expiratory flow rate, and among secondary school students, peak expiratory flow rate. And we have the school type, public and private school. We have the age, we have the sex, weight, height. Can you see all the factors that I did simple, what you are seeing here, they are simple regression. Are you following?
Yes.
Yes, sir.
Yes, because I don't want to be doing the simple regression here, but I want us to go and do the multiple regression. I just wanted to see the way the result of the simple.
Though this is not the subject of our lesson today, but this title, well, let's go on, sir. Let's go on. I was just looking at the title. You said simple linear regression of peak expiratory flow rate on associated factors.
Yes.
I would have thought that factors. I felt that the factors were the one explaining the peak respiratory flow rate.
You know the reason you are saying this. You know, yesterday you didn't come late. Now it was the first day you came late.
No, I was early. Yes, I was early.
Yes, if you remember when I was discussing the origin of regression, I said is the outcome you regress on the factor. Going back. We said from condition to the condition.
Conditioned, yes.
Yeah, from the conditioned to the condition.
Yes, to the condition. Yes.
Yes. From the cause to for the effect to cause.
To the cause.
Yes. So you are regressing Y on X. You are regressing the outcome. You are going back. Okay. You have the outcome result. You are now going back to see what are the causes.
Okay. Okay.
The regression means going back. I don't know if you understand me now.
Yes, I get you now, sir. I get you.
And that is the right way to say it. That's the right way to put it. Yes. Now, look at, you can see from what you can see from the simple regression, the one that gives you the highest R square
is height. Height.
Followed by weight. Followed by weight.
Weight.
Then
age.
Then after age is systolic blood pressure.
Systolic blood pressure.
And after systolic blood pressure is sex.
Everything
Either male or female. Then the other one, yeah, 0 point something. They are not so important.
They are not significant. Yes.
And they are not even significant. You can see. Though we have PMI share circumference that is significant, but the contribution that are very minimal. So you will be surprised when you run the regression, multiple regression. You're going to see, multiple linear regression now. You will see that height is number 1. It's not weight that is number 2. Number 2 is age. Number 3 is sex. Weight is just the last one. It sounds interesting. So let's look at the data. Let's go to the data set now. Dr. Juju Anna.
Good evening, sir.
Good evening, Dr. Juju Anna.
Fine, sir. We're waiting for you. No problem, sir.
No, hope you are enjoying what we are doing.
My wife is laughing at me. You know, so she said, whenever you mention statistics, I will start sweating.
That was why I asked you to see me before 6, because I know that I will be busy. But it's okay that you are here. And it's even okay that you are enjoying it, because sometimes when I ask you to watch, you subscribe, I say you should watch video, you say you want to finish writing. You don't know that in the process of writing, if you get to get information, you get clue to what you are writing. Many people, when you ask them to know, just to even to listen to lecture, they say after they finish their work. You know that what you are writing is that thing that makes you to make sense in what you are writing. Yes, I mean. So even some people to the extent that they after the exam,
yes, sir,
they need the knowledge to go for the exam. So look at the data set now. So let's just quickly, without wasting time, just to confirm.
Okay, my data set.
No, not you. I'm just talking generally now. We are so after I'll come back to when you finish your hand. So peak expiratory flow rate, where is it? Is the outcome? You know, that time is the big data. I didn't extract this thing.
Is it 1, 2, 3? Which one of them?
It's one. It's the one I'm using. It's the one. Now, just to confirm some things.
That would be dependent variable, sir. It will be dependent variable.
Is the dependent variable? Yeah. Yes.
Dependent variable. Yes.
I put it as dependent. So let's confirm what.
Yes. Now.
Let's just do height. Look at it.
Height. Yes.
Just to confirm. Let me share the result. Can you see? Can you see the R square?
Yes.
Yes, sir.
That's 26.9.
Yeah,
that was what we saw on that table here. This is simple regression. Yes, I mean, because that's the one that give you the highest. Okay.
After that, you're doing declaration. Is it?
So.
Okay, after the department.
Nothing again.
So you Juju, you are disturbing us. You mute yourself if you want to be talking at home. Yes. Yes. Okay. Let me go for the second one. Yeah. Just to confirm, let's look at the weight beside it. Can you see the weight?
22.1.
20. Can you see 22? That was what we saw there here. So just to confirm what I show you, then.
I think we should do the multiple now.
Okay, don't worry. Age is 18.9, right?
18.9, yes.
Okay.
Yes, 18.9.
Yeah. So no, there's no rush, don't worry. Because I want to do that sex, because the sex, you have to, it's categorical. So I
Yes.
coded because in the analysis, male has higher peak expiratory flow rate. So I now code the male 1, female 0. You understand me now?
Okay.
Yes, if let's say
Yes.
female has higher, I will code female 1. But if I
One.
even the way it is now, if I code the female 0 and female 1 and male 0, it will give me the same result, but it will in a different
Inverse.
direction. Yes. It will
Yes,
give you
it will change the
negative.
direction.
It will give you negative. The regression coefficient will be negative. Okay. Somebody is not muted. Dr. Balogun.
Hello.
Yes, you are disturbing us. I'm trying to mute you.
Hello, Doctor.
Yes. There's a noise from your hand. Okay.
Yes, I've muted myself.
Okay. So I wanted to do the sex. So
Sex.
I've already said female sex, male sex. Can you see now? I created, look at it, male sex.
Dummy.
This male sex, a dummy, yes. This male sex is a dummy. I make male 1, female 0. The female sex, I make female 1, male 0. So that's the dummy for it. Now, you may be, I don't think we should need to repeat because we have done it on the first day. The way we select. That's
no, we can go forward, sir.
Yes. Select. The way you select, you do it. Yes. So because that Dr. Kowa was raising the issue. So can you see? Can you see the 7.9?
Yeah, 7.9%. 7.9%.
Yes. These are practical issues. Look at the coefficient. Can you see? Can you see the coefficient is positive?
Yes.
Let me repeat the same thing with female sex. You will see what will happen. Instead of using that male sex, that is coded in opposite direction. Can you see the every R square is this same 7.9? Can you see? Can you see? It's not the same 7.9.
Yes, it's
the
7.9.
The coefficient is minus. It's the same
minus
value.
Now.
There is the same value 47, but it's minus.
Yes.
If you look at the T, everything will be the same thing. But the T here will be negative, but it's the same thing value. If you compare with the rest, it's the same. It's the sign that changed. Can you see?
Yes.
So now let's now go to the multiple now. Linear. Now let's start with the height, number 1. So next. So you know the weight was the one that appeared to be the next best, right? Are you following?
Yes. Yes.
So let's put the weight. Let's put the weight. Let's see what it is. That's what it will have to read. Can you see now? Can you see the R square move from 26.9 to 30? It just added how many? 3 point something.
3.1. 3.1.
3.1. And whereas his own was 22.1, weight was 22.1 R square.
Yes.
So what is telling you is that most of this thing you are seeing with weight was because of the height. It was height that was confounding for it, because if somebody is tall, it will weigh more than the person that is tall averagely. You understand now? You know, somebody that is tall looks slender, and somebody that looks short, that looks fat. The person that is tall may still weigh more than the person that looks fat, that is short. You know that?
Yes.
But the only thing, the BMI of that short person is the one that is bigger. So what is here is actually the height that is the factor. But because most of those people that are tall, somehow they will weigh more than the people that are short. You get the picture. So you're giving the impression that weight is a factor. So let's repeat the same thing now. Let us move instead of using weight here, let's use the second. Age is the next best, right? The one that gave us 80 point something. Let's put age there. Can you see improvement? Can you see
1.5?
Can you see age
Yes.
that has less R squared than weight improve the model better than weight? Does it make sense?
You said age that has.
Yes. I think it makes sense.
Yes.
That means that the level of overlap between weight and height is minimal. Is minimal. The level of overlap between weight, between height and age is minimal.
Exactly. It's
So
not as
age,
much.
Exactly.
It's not as much.
Height and age
Age is so age is contributing to the model more than weight.
Thank you.
Because weight and height overlaps a lot.
Exactly. It shows that the effect of the weight you are seeing is actually due to height.
And because of height, yes.
Yes. Now we also know that if somebody, older people, so children in secondary school, older people will weigh more than you. So, but the effect is not as much as that of the weight.
Much as that of the weight, yes.
Thank you. Thank you. Now we can try again because that's the way you do stepwise. So sometimes you know when some people they give you data to and they think maybe it's a joke. You just not to run it. For you to do good job, you have to do a lot of brain work. Begin to see.
Yes.
Which one is this? But that's why people that understand this, even if they cannot do it, they give you job, they appreciate it. But the people that are daft, even mentally they adapt in everything they adapt. When they don't even know what to do, they will not even appreciate what you are doing because they don't know. You're laughing. That's why. And they will even say that they don't have the money that how much I cannot pay that because they can't appreciate the work you are doing. So poverty is not only and it's mental poverty. Mental poverty and physical poverty, they are related. Okay. You are laughing. Let's try. You are laughing. I want to remove the age. Let's try the sex. Let's see the contribution. Maybe does it contribute better than age? Let's try first before we proceed. So I remove the age, I put sex now. You will see that its improvement is 30.9.
30.9.
So you will see that it's not as it has not contributed up to age, but it still contributes better than weight. Are you following? It still contributes, it's still possible better than weight because the weight accumulates in 30,
Yes.
and this one accumulates in 30.9. I don't know if you understand me. Are you following?
Yes.
So weight, when we put weight, it gives you 30. But when you add sex to height alone, it gives you
height.
30.9.
You have 30.9. Yeah.
So it's even telling you that even sex is even better than weight. Still. So in this case, male have better expletive flow rate than female, because that's what it's telling you. So let's now go back so that we put the age there. So we are from what we have done now, we have established height as number 1 and age as number 2. We move forward.
Yes.
So we want to know the best. But you see the next best is X. But let's still put the weight. Let's see what it will add to that something. Bro, let's still put the weight. So that I won't know as if we are discriminating against weight.
Okay. It's not discriminating against itself.
So let's look at it now. So if we look at it now, from 31.5, which is where the age and height, so it has improved to 32.8.
Yeah.
So what is the 32.8? What additional thing has it added? 32.8. Let's
13.
now
0.13 13%.
So
No,
just note this.
0.13.
Just note this 32.8. Let's replace it and put sex now as number 3 to see. Maybe it will be better than 32.5. So now put that sex.
$36 is better.
Can you see? 36.1. Can you see?
36 is better.
Can you see? Can you see it had up to about 4 or 5?
5.
Opposite.
4, yes.
So
5.
Can you see? Can you see the logic? So, so the next one, you know, we didn't talk about systolic blood. If you go and add systolic, that one is, in fact, it doesn't even have anything reasonable because the systolic was greater than sex now. Should we try systolic blood pressure? Let's try systolic blood pressure because that one also, because that one also has a big R square. So instead of sex, let's just put systolic blood pressure. Yeah, this is systolic blood pressure. Can you see 32.2? Can you see now?
32.
So, yeah, so it didn't even contribute up to weight. Can you see?
Even weight is better than it.
Thank you. So, so you can you see now? So we go back to the sex as number 3. That's how to do multiple regression. So we now put sex. Then now let's go ahead now. Let's put weight to see what it will give you. The addition weight after you have already put sex now. Let's see if weight will be number 4 or systolic blood.
Okay.
Or systolic blood pressure. So let's see what is going to add. So from 36.1, I've increased to 38.4. That is the weight. Can you see now?
8.4.
Yeah, 38.4.
Yes.
Let's replace it with systolic blood pressure. Let's see if it will do better. So that's where we're going to stop because those are the things. Every other thing they didn't even contribute anything reasonable. So let's try systolic BP. Can you see 36? Can you see? And that one was 38.
Yes.
So it shows you that weight is better, right?
Better, okay. Yes.
So we now put weight. But now after weight, let's see.
We can now put systolic blood pressure.
Exactly. To see, does she now add anything reasonable?
Now add more. It's lower down. Yes.
Yeah, I've seen it. Can you see? You say 38.6.
Oh,
so
it's not reasonable. 38.5 to 38.6.
Exactly. So that was why all those exercises I did that now made me okay to now build the model. Let me just show you the word. So that's where the model is height, age, sex, weight. Stop at weight. You see it now.
Okay, you stopped at weight. Okay.
Now, because
you need to include the SC.
No, I didn't include.
It's small.
Okay, it's very small. Okay, yes.
It's very small.
Yes.
Okay.
So if you, so all those other ones, they are not contributing any much. So
anything.
So look at it now. The percentage, the way. Look at the.
But excuse me, sir. You didn't include sex too. You didn't include sex.
Sex is there. Look at it now.
Okay. Sex is there.
There are 4 of them. So the way you do it now, you now say for the.
Okay. No, I was looking at the model down. Okay.
No, you know, I split into male and female. In the equation, you have to now split it into male and female because
male and female
is a categorical. Is categorical variable. That's why
variable. Okay.
Separate variable. This
okay.
It's very equation.
Okay.
It's the same thing. Yeah. So you will see it now. You will see for the step 1, the R square. Can you see? You do the model, the R square. This is the beta. The beta for this one. Then the beta for each of each stage, how the beta increases. Then the R square for each of them. Can you see the F ratio also and the P value? So at the end of the day now, the model, what you are going to code for the model is for that one, the R square. Look at the beta. You now code because their beta also change for each of them. So is the step 4 you are using now. Can you see the equation for male? PF 2 height. Look at the coefficient for height here is 2. Can you see?
Okay.
The coefficient for height is 2. That's 2 height times height plus coefficient for
7.8.
Age is 7.8. For weight is 1. For weight, can you see? 1.7. No, but you cannot use the same thing for. You cannot say 40.7. Can you be calling
for sex? No.
So what you do is that when you now incorporate that thing, is now, you know, if it is for 40.7 is for male. I don't know if you understand now. If it is female now, is a negative something. So what we now do is that for male, you now the constant. Look at the constant. The constant is minus
192.
Exactly.
192.9.
If you put this 40 point something, you add it to it, it slashes the constant back to this.
Okay.
You get the picture now?
Yes,
so
yes.
For female, it's the same constant. You put the 1 minus 192.9. Can you see?
Yes.
Does it make sense? Because what that 40 point something is telling you how many times a male is more likely than a female. The value is for the male.
Okay.
Can you
male,
see?
Yes. Okay. Yes. Okay.
If you remove that 40.7, that constant, this value, what remain here will be 152.92. But you don't need it for the female. That 40.7
female, yes.
For male.
So that 192 remains.
Yeah, 192 remains. So that is
yes, female was a reference. Yes, Dr. Ogo. Thank you.
So that is how this is the equation. And this thing will now develop a monogram. A monogram. Use this equation to, it's not a small job. In fact, the monogram, let me even show you. The monogram is so bad that not be small, you know.
So how much did you collect? How much did you charge for this?
The girl was a stupid girl.
I said, how much did you charge for this analysis?
I didn't collect more than 150,000. And the girl was
okay.
So she can change. And the girl, and you know, sometimes you don't even know the anonymity of the work. You examine until
work, okay.
Because the issue of nomogram is the assessor, because she went to fail. She went to fail and now the reason, let
with
me
this type of analysis.
What I say, she is doing. The lady is doing master in UK now. You know, the guy wanted to do a good job. You know, the type of examiner and the assessor they have and the teacher they are not as advanced as the work is doing. So if you see even the examiner, if you see the comment, show that the examiner does not know, in fact, is half informed. And it's not, you know, it's better not to be informed than to be half informed. So the examiner was a half informed person. These are the okay, let me show you this. So she failed, but at the end of the day also, she said she learned a lot in the process. She now went back and do the exam back, and she now passed. She failed not because the work was not good, it's because the examiner was not competent enough to understand our work. And you know, since examiner is examiner, so it's the one that determines if you fail or pass. So this is the mono. Can you see? So for each of the age, for weight, height, can you see what I'm showing?
Yes.
Yes.
How did you generate this, sir?
From the equation and Excel now. Look at, I put, you know, if you look at the factors there now, sex is there, height is there, weight is there. So I now put weight, some value of weight in one.
Okay, you substitute.
Exactly.
So all this 100.
You do substitution for that equation.
Exactly. So you look at it for male, female, for the height. Look at the height from this. The height is from 100 to 185. Then
to 185.
Yeah.
Then for age 10,
kg 12,
weight 20. Female and male.
Exactly. For then age also. Look at age 10. Can you see? Age also. Age also.
Yes, so.
This is like doing a 4-figure table. This is like doing
so the values in this box now are the
for the peak,
PFR.
Exactly.
For each age
height.
With
sex
height, with the sex.
Wow. Yes.
Height,
so
yes.
When you check somebody's sex in the age now, you look at the kg. If the person is 40 kg, male, female. And what is the height? It's a 150. That's a 277.
Okay.
That should be the normal for the person.
Normal for at least for this environment.
Yes. Because the work was done in and the sample size is big though. 9 around something. So
that's serious.
He did
so
it
it's very reliable.
Yes.
Wow.
So that's just it. So all those things is combination of so it's quite interesting if you know how to run regression, multiple regression. It give you first hand. And once you understand the equation, and you see now from the first principle, you understand the equation, and you know how to do all those things. Simple. So that's just it. I don't know if there's any question. Any question?
Thank you very much.
Then the other one, maybe I should even run maybe to close is that data set we use for ANOVA to demonstrate that the ANOVA and regression is the same. I will do that one. That will be the last thing you just do for you to see. Of course, you have already even known because there is a table of ANOVA in every regression. But I just want you to have a data set that you use to do ANOVA and you see the result and you run it as a regression, you see the same result without anything changing. So it makes you to know that ANOVA and regression, they are two faces of the same coin. They are the same thing. Okay, I think let's look at it. Somebody want to share that one because you have it. Libido, the Viagra. I think let me go and look for it. Let me go and look for the data. Let me look for the data set. Just 1 minute. Yes, I have opened the data. So can you see the data set?
Yes, sir.
Yes, this data set on
yes, sir.
On libido among the 3 groups for ANOVA, used for ANOVA. So if you look at, if I show you the labeling, the dose, this is the libido score, the second one. The dose, we have 3 groups, there are 15 of them, 5, 5, 5. Placebo group, 5. The next one, low dose Viagra group, second group, and third group, high dose Viagra. Those are the 3 groups. Now, for when we run our ANOVA, you just need this libido and the dose, that's all. But I created this dummy variable for the regression. So when we were doing ANOVA, we didn't use it. But everybody that has the file, the dummy variable is there. Now, if you remember, because there are 2 doses, 3 doses: placebo, low dose, and high dose. So we now made, if there are 3 categories, you have to create 2 dummies. So the number of dummies is 1 minus the number of categories. So we have dummy, the first dummy, you are going to make 1 category a reference group. So in this case, we made placebo the reference group. It makes sense because last week Dr. Babagana was asking, why didn't we make high dose? When you are trying to look at things, placebo, low dose, high dose. If you are to make, you expect the libido to be higher among high dose and followed by low dose. So the placebo. So if you look at the logic behind plan contrast, we did that when we were talking about the workshop for ANOVA. Plan contrast is the same logic. You expect the libido to be higher among the high and low dose. So to make the placebo the reference. So it doesn't make sense for you to make the high dose the reference. But if, let's say, it's the other way around, you can make the high dose the reference. Anyway, if you make the high dose the reference, you get the same result, but the interpretation will be upside down. No, it's going to be upside down. It will be just like the way the decision of making male 1, female 2, and male 1, or male 0, or whichever one. It depends on the way you want to interpret. Well, it give you the same result, but the interpretation will be, the way to interpret it that differs slightly. Now, so that shows that we are creating 2 dummies, 1 for low dose and 1 for high dose. We are making placebo the reference. When you are creating the dummy for this first dummy for low dose is only the one that are low dose that will be 1. Every other thing will be 0. Because the dummy is about 1 and a 0. So the one that are 1, the group that are low dose, because the dummies for low dose will be 1, the rest will be 0. The dummy that is for high dose, all the one that are high dose will be 1, the rest will be 0. The implication is that in all the dummy, the reference group will be 0. And that's what you can see now. The 2, the reference group placebo is 0. But for the other one, the low dose is 1. Yes.
That means that in that reference, that means in the dummies, the reference group is equated to the second group. Hello?
No, it's not equated to any of the second group now. You create dummy for the other group, the reference group, you are not creating dummy for it. That's what it means. If you have 3 categories, you make 1 reference and now create dummy for the other one.
Okay.
Yes, when you are creating dummy.
So what I'm saying that your analysis is towards the 1.
What do you mean by towards
you are
the
not? I mean, you are looking at
the same.
What I was thinking is that
the value is the same for placebo and high dose.
High dose.
0.
Yeah, 0, 0. That's what I'm saying. Does that mean you are equating the group?
No, you didn't get it's because you didn't get the logic of what I was saying. If just listen again, you are creating a number of dummy 1 minus the category. In that sense, you are making 1 category a reference, and you are creating dummy for the others. So,
okay.
If you for example now, the low dose, the category for that should I'm creating dummy for low dose and high dose here, because the placebo is a reference group. I'm not creating dummy for it. In the dummy for a particular group now, those ones that fall under that group, they will be 1. Every other one will be 0 for that dummy.
0.
That's what you are just seeing now. For the dummy that for low dose dummy now, first dummy you see low dose. All those ones are low dose, they are 1. Every other thing, either high dose or reference or not, is 0. So, but the dummy for the high dose, all the high dose are 1. Every other thing will be 0. You get it now. And the implication of that is that whichever dummy, the reference will be 0 in all the dummy. Yes, now, if you look at it now, the placebo is 0 in all the dummy. While for the other one, It is where they are the dummy that they'll be 1. They'll be 0 in any other thing. That's all. It's very simple now. If you are a pastor,
Yes, it's simple, sir.
when you come to church, everybody will be, hey, pastor is the number 1 in the church. If you are a doctor, when they get to the hospital, even if pastor brings his own wife to the hospital, children, it's the doctor that is the rally point in the hospital. You will get the bishop now. So it's the same thing. If you get to the military, if you are a doctor, you are just one of those ones. You are not a combatant soldier. So you cause 0 there. The combatant soldier is
like
you get it
like
now.
me, sir. Like me, sir. I'm working in the law school. I'm just one of their staff.
You are just
the lawyers.
Yeah, the lawyer is the number 1.
Zero.
You are 0.
I'm 0. I'm 0.
You are 0 in the law school.
Yes, sir. Yes, sir.
You are 0 in law school.
0 there.
But when lawyer, someone that is legal advisor in the teaching hospital is 0 there. You cannot.
It's 0 in the yes.
Just there, yes, that's just it. So that's if you
That's
can.
it.
So that's just the principle there. So now let's look at the way we run it now. So is this dummy we want to use for regression? You are not using all those ones. You are not using the dose.
Okay.
You are not using it. So you are using the placebo to get libido and the dummy. Because this one now, the dose now is for when you are doing your maybe normal ANOVA. But if you want to run it as a regression, you have to now, you have created this dummy for that dose. So, okay, let's first of all do the ANOVA first so that you see the way it comes out. Compare means one way ANOVA, libido as the dependent list, dose as the factor. You know where is ANOVA we are running now. So
yes.
So let me share the result. So can you see?
Not yet.
Can you see?
Yeah.
Yes, we can.
Yes, you can see the result. Yes. Very simple. You will see sum of squares. You will remember.
Yes.
Total sum of square is the one we are talking of here. This sum of square between is the sum of square explained by the model. Sum of square within is the one not explained by the model.
Model.
Look at. Okay, so it is exactly what we did yesterday. But let's just run this one as let's see as regression. Now you go to see. So libido, okay. The 2 dummy will be the dependent variable. Can you see? Can you see this table ANOVA? Is it not the same thing you are seeing?
Yes, yes.
Sum of square.
Exactly.
The regression in the other one say between group.
Yes.
Is the same value. So the residual in the other one say within group. The total is still the same. So this is the total sum of square. That is total variability to be explained. The residual, this is the residual, what the model cannot explain, which correspond to within group in the other one. This is what the first one is what the model can explain, which correspond to between groups. And all those, the degree of freedom is exactly the same. The examiner. So if you go to the first one, look at this, the ANOVA, the first one, first for run. Because there are 3 groups, the degree of freedom for the group is 3 minus 1, which is 2. Within group, the degree of freedom is 12 because there are 15, 5, 5, 5. Each there are 3 groups. Each of them is 5 minus 1, 5 minus 1, 5 minus 1. That's 4 times 3, 12. Because all of them, the total degree of freedom, because there are 15 of them. 15 minus 1, 4. And when you add these 2 degree of freedom, they still give you 14. 2 plus 12, 14. Can you see?
Total.
Yeah, total degree of freedom. And when you look at, you want to calculate the mean square, which is the variance. Because this one we have here is the sum of square. You know, you have not calculated the variance. The variance is sum of square divided by the degree of freedom. When you divide this 20 by this, it give you 10 point this. When you divide this one by the 12, it give you this. This is the variance between, which is the model. Then divided by the variance within. So this upper one, the variance, the model can explain. This one is the variance, the model cannot explain. When you divide this by this, it gives you this. That shows that the what it can explain is 5 times more than what it cannot explain. And it's and if you run this as a regression, it gives you exactly the same thing. Look at it. So if you want to explain the degree of freedom in the context of the regression, 2 here means there are 2 factors. You know, there are 2 dummies you created. Are you following?
Yes.
There are 2 factors, 2 dummies you created. So because they are serving as 2 separate X, 2 exposure variable, 2. You get the vision now. And this residual, the residual degree of freedom is the sample size minus the number of factors
minus 1.
Minus 1, which is the bit, which is the constant. Yes, I'm now. Because the number, if you now make it 3 now, because we have 2 factors. That's why you can see now the coefficient down. Can you see? You have 3 coefficients here: B0, B1, B2. Can you see? B2. Yes, now, because there are 3 constants here now. The one for the constant and the 1 and 2, as if there are 2 factors, there are 2 predictors, X here. So when you remove the 3 from there, it gives you the degree of freedom. Can you see now? And the total degree of freedom is sample size minus 1. So it's the same thing. When you can divide this by this, give you this here. So when you divide, so can you see it's exactly the same? So the only thing, though I explain all this other one, the coefficient now, I explain it to when we're doing the regression. We're doing the ANOVA. If you see the 2.2, if the data set, the people that were in the ANOVA class, the placebo group, the mean libido was 2.2. So you know the one you make constant, you make as the reference is the constant. This 2.2 is the mean for the libido group. This one is the difference between the B1, the difference between the libido and the low dose, because the mean for the low dose is 3.2. When you remove 2.2 from 3.2, give you 1. And this 2.8 is the difference between the high dose and the placebo.
And the reference.
The reference, because the mean for the high dose was 5, is 5. When you remove 2.2, it gives you 2.8. So I think I show a graph. Then let me show you before you just close. I show a graph that just showed this relationship when we're discussing this thing then. Just 1 minute. ANOVA, Victoria, one-way ANOVA. Just 1 minute. Okay. Yes, let me show you now. Yeah. Can you see? Can you see the graph I'm showing? Hello? Yes.
Yes, sir.
Yes, yes.
So this is something that is explaining. The try to plot is the green circle placebo, the triangle low dose, the square high dose. If you plot it, the mean for the placebo is 2.2. Can you see where it is now? This line is the mean. And these are the different, the 5 value. 3 were below the mean, 2 above.
Okay.
Yes. This is the mean for the low dose, so 3.2.
Low dose.
And 3.2 per it. And there are 3 values below it and 2 values above it. This is the mean for the high dose, which is 5. There are 2 values above, 1 value exactly at the mean, and 2 values below. This is the grand mean. When you add all the 13, 15 together, it gives you 3.5 something, 3 point something. No, yeah, around 3 point something as the value. This 3.75, 3 point something like that. 3 point something as the grand mean. And that grand mean, if you add all the 15 together divided by 15, give you, or you add all the 3 means together divided by 3, give you the same. So this dashed line is the grand mean. So is the grand mean, the other 2 means are below the grand mean, the other means above the grand mean. So you see B1, can you see B1? B1
yes.
Is that coefficient 1, the difference between the placebo and the low dose. Can you see?
Low dose.
You know the placebo, the mean is 2.2, low dose is 3.2. So remove 2.4 from 3.2 is 1. This difference between these 2 mean. And this B2 is the difference between the mean. Who is making noise? So the difference between the mean of the low dose, which is 2.2, and the high dose, placebo, which is 2.2, and the high dose, which is 5. So this different B2 is 2.8. That's what you see in the regression line. Does it make sense? Hello?
Yes. Yes.
Yes, that's just it.
Yes.
Yes, yes,
it
yes,
does.
yes.
So I think we can close here. Unless there's any question.
Yeah, thank you very much, sir.
Very much, sir.
Thank
Yes.
you.
Any question?
Thank you very much, sir.
Welcome, sir. Yeah, thank you.
Thank you, sir.
Okay, welcome.
Thank you, sir.
Welcome.
I just want to ask this. I saw that we were.
I'm not. This is not clear. That your hand is not clear. So say again. We cannot hear you very well. Your distance is cracked.
Those conditions. Sorry. My network is not very good.
Okay. Well, let's talk now. Let's see if we can hear you again.
Are you talking about when you are
Can you
talking
quickly
about
chat it?
Hello?
Maybe you can chat it.
Can you chat it? Can you chat it?
Okay.
Okay, Prof. Good night, Prof. Okay, you can chat it.
Good night, sir.
Good night.
Good night, sir. Good night, sir. Good night, Prof, sir.
Good night. So you can wait till he's chatting it. So you can, if you want to wait for, he's chatting the question.
Well done, sir.
Okay, Dr. Friday, just wait a little bit. So
No
you
problem,
can,
sir.
yeah, just wait so that we can just close this session. Okay, correlation between dependent variable in the regression model. Yes, we talked about correlation between dependent variable. And what aspect? We talk about multicollinearity. If both of them perfectly correlate, it's not good. So they'll be serving as one variable. So you only include only one. You don't feed it two variables that perfectly correlate with one another. That's multicollinearity. But Dr. Balogun, can you hear me? Dr. Balogun?
Yes.
So, okay.
Yes. Are you seeing the question I'm trying to ask?
Yes. Now that's why if you look at it, we did the correlation. That was why we first of all did correlation for most of these things before we even go ahead. It's good to correlate them to see. if there's anyone that perfectly correlates. Because perfect
So if you
correlation
have the
means
ones
that,
that are perfectly correlating,
eh?
if you have the ones that are perfectly correlating, you exclude the two.
No, you don't exclude the two. You include one. You have to know which one is a factor per se. You have to decide which one is a factor to include, because it means that both of them are doing the same thing. So you can even put it there, call it different thing, because they are doing the same thing. So you just include one. Okay. Any other one? Okay, no problem. I think we stop here.